morning, good afternoon again, and thank you for coming to our seminar. Today's speaker is Gerardo. I think most of you know him very well. He's been with us for 2 years now. He came from Mexico. He did his PhD in the University Nacional in Mexico, in Mexico City. And he did his PhD thesis on gamma ray bursts and their properties and structure. And here he also specializes in gamma ray bursts in my group. He did projects about non-gamma ray burst jets, but also an additional topic appeared recently was the gravitational wave signals from the GRBs, which he will hopefully cover here in this talk. And this part was supported by the Young Researchers Project last year. So welcome, Gerardo.
Thank you. Yes, thank you everyone for coming and organizing for encouraging me to give this seminar. Yes, I will be speaking about of the numerical simulations mainly of gamma ray burst jets. Yes, as Agnieszka said, I am from Mexico and I have lived here in Warsaw. So, we are happy with the snow. We have the snow. Yes, first of all, let me speak starting from scales of these objects, because yes, several times in this colloquium we have different topics from quantum mechanics and cosmology, different opposite scales, and I have to say that our scales are in intermediate. Our main actor in this kind of topics is solar mass black hole and accretion disk. More or less, this the system size is about 10 kilometers. It's more or less the radius of one city. Warsaw, roughly speaking, it's about 12.5 kilometers, more or less. That means that's a circle. But more or less, the computational blocks, if we want to study these objects, have to cover the size, and the resolution have to be more or less 1 square, for example. But the history is not finished here because from this system, accretion systems, we have strong winds coming from the accretion disk and relativistic jets launched as a very intense flux by the Blanford-Snide process. And yes, I will be speaking about long GRBs, which are jets arising before the collapse of massive stars. And one important scale is the iron core of the star. The iron core is more or less 10 to 8 centimeters, and it's more or less the size of Europe, or more or less the size of the Earth. The radius of the Earth is 10 to 8 centimeters, between 10 to 8, 10 to 9 centimeters, and we have to cover in our simulations this resolution, no? And it starts to be challenging because we have to preserve the enough resolution as a city or a square inside of the city, just for follow with very accuracy this kind of events. And the history is not finished here. Well, yes, the iron core collapse. This is the star that I am speaking about. This is a cartoon of a regular massive star, which eject the outer layers, the outer hydrogen layers due to the fast rotation and strong winds. And the structure more or less before the collapse is showing in this cartoon. The iron core, the outer layers, and this collapse into a black hole. A powerful jet is launched, and as I told you, the history is not finished here. The jet is start to expanding inside to the star, and we have also to thinking about the size of the star, which is 10 to 10 centimeters, more or less. The history is not finished here because when the jet breaks the surface of the star, it is still propagating in the interstellar medium, and more or less, the distance that we have to consider in this kind of studies are 10 to 13 centimeters because, roughly speaking, again, is enough distance in which the environment becomes optically thick, optically thin, or at this case, it's possible that the photons produced during the emission of the shock front of the jet can escape from the environment. So starting from this distance, we can do estimation of radiation. But before that, we have to construct or modeling the evolution, the entire evolution of the jet. So as you see, these events are multi-scale. It's a multi-scale problem, and we are now working in just connect this event because typically the methodology is solving by parts, not all together. Yes.
What is the reason why you keep to measure this astrophysical distances in centimeters?
Convention, yes, sorry. It's just a convention, yes. I am thinking in centimeters. People think in parsecs or parsec, well, yes, fine, yeah. Or technical.
So you need to use meter, not centimeter.
Well,
Astronomers still use.
yes, I don't know. I learned from PhD. Yeah, sorry. Yeah. Yes, it's a tradition. Yes, it's not the best, but yes.
And some other things.
Okay.
Yes. So, yes, also for this reason, I am comparing with some objects that we know. No? Yeah. Sorry. Yeah. This science is made in this way. Yes, and also, well, cosmic explosions. No? Yes, I added these two examples because, well, two reasons. One, the first is because are my favorites. But yes, I have to say that frequently I will be mentioning a jet. A jet is a ejection before an ejection and coordinated. And basically, it's a gas propagating. No, this jet is produced during a protostellar event. Here we have a baby star. It's a new star forming. And here is the diet of star. This is a remnant of supernova, and we have different kind of explosions. But well, also I have to say the second thing is this kind of explosions. The propagation of the velocity of propagation of this gas is about the speed of sound, and it means that you can take these objects are projected in the sky, and theoretically, you can take a telescope and look for the coordinates and take a photo, and analyze. Well, it's more difficult that to do that, but the important thing is these objects are projected in the sky. However, we have another exciting events in which we are working called transients. But these events, the difference between the previous slide is you cannot take a picture directly from these events. No? This is an acoustic image, but for these events are related to accretion process, gas accreting in compact objects, explosions of stars, gravitational waves. And nowadays, the people is working in two kind of signals, gravitational waves, electromagnetic counterparts. Now it's the new way of to astronomy, complete information from another non-photonic signals. This kind of events or gamma ray bursts that I will be speaking about is some kind of one night stand or a shooting star. You only have a few seconds to see this event, and you have to extract all physics as possible from very few seconds, and it starts to be challenging. The explosions are take place everywhere in the sky. This is 1,000 of GRBs detected isotropically. And the emission of a typical gamma ray burst is in this way. This is the Milky Way in gamma rays. And the burst just it's very luminous. Indeed, this kind of explosions are the most luminous explosions so far. No? More or less in order of magnitudes and luminosity. Again, it's doing in a CGS system by Earths. It's about 10 to 53 Earths, or 20 orders of magnitude more than the sun is shining now. The light curves typically present variability, and every light curve detected from GRB is different. Yes, this is nerd reference, but you have to be you have to put very much attention, no, in the event, because probably you cannot see again the same thing. We understand that the variability of the light curves is due to the shock collisions of every working surface of this relativistic jet. Basically, we can get different sources of radiation, but the jet emission is the most efficient. Basically, when the collisions take place, the dissipation of the energy is just the emission. And we have different collisions, and it's the reason of this variability in the light curves. And also another thing that constrains the observation of GRBs is the fact of the emission, is the shock take place in the shock front of the jet, and it is traveling very fast at relativistic velocities, and we have these dimming effects. No, when the jet is propagating very fast, the radiation is collapsing in a point, or we have a restricted region in which we can see the jet. For this reason, almost all GRB observations are on axis. And we are looking in the future for more off-axis observations or detect by gravitational waves GRB jets. However, yes, also since we are in a city that has snow, the jet shock front, you can imagine the shock front of the jet that it is filling up material from the interstellar medium, and while the shock front gets enough mass from the interstellar medium proportional to the initial energy, the jet starts to decelerate in the interstellar medium, and the velocity is decreasing, and we have another regions to observe from the jet. Yes, and for this reason, we can observe another electromagnetic counterpart from these gamma ray bursts, following more or less this strategy. The bursts take place now in the sky, and we have nowadays two satellites that detect this kind of events. The satellites know the position of the explosion and send an alert to telescopes in the Earth. The telescopes can focus in the region of the explosion and can follow the afterglow emission. This is typically the afterglow emission. In the sky, we can see, for example, this kind of image. This is the position in which the bursts take place. Here is not happening. Here happened, and the brightening is decreasing. No, speaking, and the whole emission of the GRB is in this way. The front emission in gamma rays and in another frequencies we can observe in another frequencies. X-rays, optical, and radio emission, the cooling of this blast wave. Yes. Okay. So far, I mentioned how the emission of GRBs are, and well, now let me say something about the progenitors. Mainly, these jets are produced by binary neutron star mergers or binary black hole neutron star mergers, or the collapse of massive stars. For observational reasons are called short and long GRBs, but nowadays we are trying to change this definition, because we In the last years, we have observed new sources coming from binary mergers and that are long lasting in gamma rays. But basically, those are the progenitors, and we have another exotic GRBs that probably are originated in the same systems, but with some different physics. I mean, these jets are produced because take place in high magnetized systems, but probably this another observations could be produced by failed jets or a similar explosion, but less energetic than these jets. Okay, let me start with my favorite part, which is the methods and the things that we are doing. We are solving gas dynamics, and for that we have to solve this set of three equations. Here I added a bridge between the easy way and the most difficult way. These equations are the conservative equations in a special relativistic way. The mass, conservation, momentum, and energy, and it is closed by a equation of state. It could be many times it's a polytropic equation of state. And if you this quantities in red are the Lorentz factor. If you set equal to 1, get to the classical equations. And if this system could be more complicated, if you are source skilled, for example, here you can add gravitational forces, viscosities, and here radiative losses in energy, another equation of state. And you can also do in general relativistic way, just in the differential operators you add the geometrical terms. But basically, we have solving this set of equations, well, we solve this gas dynamics. We can rewrite these equations in this formalism, which is a vectorial way. It's called the Valencia formalism. And basically, for example, for two GRB simulations, we impose strong shock conditions.
There is some mistake in the indices in the formula for F.
Yeah, probably I did a mistake. But yes, where is the mistake? But yes, generally speaking, we have to integrate this set of equations.
You have two i's on the right-hand side and only one index I on the left.
Yeah. Sorry for the mistake. Yeah. Okay. Basically, for we are the way of integrate this kind of equation is using finite volume methods, and we are interested in solve explosions. Basically, the vector u is dependent on the fluxes. We integrate in space and time these fluxes, and basically we are the most main science or the most main methodology we have to take care in the discontinuity, because we are speaking about explosions, and basically for one explosion we have different velocities. No, the shock front has a crazy velocity, be the speed of sound or reach or close to the speed of light. Pre-shock density, pressure, and the static environment, or the environment in which the shock is propagating. We typically get this structure. This is the one-dimensional structure of the shock, and we have to reconstruct this discontinuity. It is very hard, but nowadays we have different methods to reconstruct these discontinuities. If you are interested in that, yes, typically we use these methods, Harden-Lux, Van-den-Leer contact methods, Fortran, or whatever, see? It's mine or sorry. Okay. If you are interested in that, I have a toy code in my website. This code is you can play with this if you are interested in that. This is a spherical 2D explosion, and you can see here the shock front is propagating. Or here I did a zoom, or here I set the propagation of the shock only in one direction. And it is funny because you can see the shock from propagation and the forward shock propagation and the reverse shock. It's hitting the gas side, and also it is propagating in opposite way. But for do real more accuracy science, we are using these codes, hard code who solves the accuracy process. You can check in the repository of Professor Janu. This code can follow the gas composition. We are using also code Mescal, which is adaptive mesh refinement code. At the beginning, I was mentioning the fact of we need very accuracy in the resolution of the space, but it's so crazy follow the same resolution everywhere, no? Because if you remember, my system starts from the scales of a city and ends beyond to the solar system. So for that, we use this kind of techniques, which is called adaptive mesh refinement techniques, in which the cells are refined, in which we have gradients, no? Gradients of density or turbulence. And they're refined in places in which the fluid is in rest. No? With this kind of technique, we can solve very long distance. And we are using now back code who has a combination of both methodologies, no? Accretion and adaptive mesh refinement. Okay, let me go to the long GRB simulation that I promised to present. Okay. So I told you, long GRBs are arising in precolossal massive stars, and is a multi-scale problem. Okay, yes, let me start with our spherical code. But yes, here I have to say as well that I don't like this cartoon because present the whole evolution of the jet. Sometimes the people thinking that the whole process presented here take place at the same time, but not. First, we have the propagation of the jet inside of star. After that, at 10 to 15 centimeters, the gamma emission, and more late the afterglow emission. But yeah, let me go to spherical code. For studying this problem, we isolate the whole universe, and the jet launching. So some years ago, were studied only in focus in the central engine. No, this puzzle is solved by parts. No, because it's so challenging. No. And for example, this the model of collapsar that started in 1999 by Fizyki, and they show that fast spinning black hole is inside of the collapsar massive star, and open a channel, and its engine is launched in this central engine. Years after. The people start to do more accuracy simulations with starting from a magnetized core in the star. They said a high spinning black hole, a magnetized core, and a jet could be launched with this in this range of magnetic field. Yes. And also another kind of studies that I was involved with as well.
What is the meaning of X, O, and R? What are these particles?
Sorry?
You have particles gamma, X, O, R. On this slide, you have particles which are called X, O, and R. What are these particles?
First, to the frequencies. We can see emission in gamma rays, X, optical, and radio emission. But also, I have to say that I am not evolving the particles.
Are these particles? What are they?
This is frequency of electromagnetic emission, X, optical, and radio, and gamma. These are all photons.
Aha. Okay. So
Well-
this is all electromagnetic radiation.
Yes, exactly.
So
Yes,
I have a question.
I am not familiar with this notation.
Yeah, it's just a frequency.
Okay, you show the system of equation for gas. Everything is in terms of gas. And now
Yeah.
finally you have radiation. So where is Maxwell equation or something? Connection between gas and radiation.
Yeah, this is by processing, post-processing. Well, first of all, I have to say that our system is, the length of the system is greater than the mean path, no, of the electrons. I mean, we are solving long scale systems, only fluid. For the particles, well, typically we assume by post-processing. We made the particle by analytically, and we assume that in every parcel of fluid, we have a population of electrons that follow the Fermi distribution. And from that, we typically estimate the synchrotron radiation. But yes, in this way, yeah.
So everything is synchrotron radiation?
Yeah. The synchrotron radiation, the observations are according to synchrotron. We can see another effects, compound scattering, but yeah, the simulations.
Keyword is synchrotron and radiation. That's what I want. I wanted to know how they radiate. Okay, thank you.
Yeah. Thank you. Another aspect of how to solve this jet propagation is excluding the central region and launch the jet a little bit far from the iron core of the star. We implement the jet by hand by strong jump conditions, and we can follow the jet evolution for larger distance. This is an example of 3D simulation of one of our colleagues. I have to speak more about that because I was related to this kind of methodology. This is with the jet implementation. Yes, a cartoon. This is the stellar profile, recollapse, the density versus radius, recollapse of massive star. More or less, the initial conditions are injected here, and the jet propagates in this region. Yeah, this is a video that shows how it's working. The jet is start to propagation inside to star, get the breakout, and in particularly this. Well, these axes are, I am showing here density, and the axes are normalized by the speed of light. We have seconds here. The measure is in seconds. You can multiply by 10 to 10 and get the distance in centimeters. More or less, we finish 10 to 11, 10 to 10 to 11 centimeters here. But it's quite long distance. This is more or less the final structure of the jet once start to propagation in the interstellar medium. And yes, we can explore different distributions of energy at the launching point, and we can see different propagation of the jets. These initial conditions are very sensitive to the energy distribution at the beginning. We can get these blobs, of recollimation shocks are responsible to the variability of the light curves, and we can get another more collimated that present less, are more stable. But yes, the connection, the distribution of the energy is connected with the central engine activity in the accretion process. Yes, this is, for example, quantitatively extraction of how is the distribution of the energy of this jet along the the angle. Yes, now let me join both regions, no? Because so far these simulations starting far from the black hole. So for that, for joining the both regions, we are now working in a new set of simulations. We took a pre-voltage massive star before its collapse, and we set by hand a black hole. No? And we assume that the material has a single rotation and a dipole as a magnetic field, and the magnetization is about 10 to 14 Gauss. And here I added a video to show how the inner layers of the star are falling to the black hole. You can see the arrows. This is a map of velocity. Blue and red lines mean the direction of the velocity. And here you can see how the central engine is activated. Here the magnetization, the magnetic flux is increasing due to the Blanford-Snelling process. And here from the center, we start to launch a jet, but the layers of the star are still falling to the black hole. We need very, very high magnetization just for drill this star because it's very dense. This is another video that I have to show. So our new simulations. This is the iron core. This is the I am showing two different perspectives of this simulation. This is in orders of the scale of iron core. Here is the half of the star, and here is the surface of the star. But it's the same simulation. Here it's take place very fast because we have thousands of frames for make this video. It's a quite expensive simulation. Here we have this is a density map. So in grams per centimeter, sorry. And we have dense material falling to the black hole, but the magnetization track to open the jet open a channel, empty region. Here it's more successfully open, and here we get the breakout. We are following the evolution of this accretion process with very, very, very long time. Here you can see a scaling of in seconds, but in gravitational times we are solving 500,000 gravitational times, and the aim is reach near to 2 million. Okay, we are testing different progenitors from Mesa code, which is a one-dimensional code who solves the equilibrium equations for the star evolution. These models came from the literature, are very famous in this science, are performed by Fizyki. The inner structure of the star it's given by a different composition, but so far we are not estimating the chemical change in the star, just only the hydrodynamical evolution with one gas spike. Here also is interesting, follow how the layers of the star is falling in the black hole. Here I am showing you different foot slices in different angles. This is this blue and dashed line covers the central region of the jet, and the opening angle of the jet is just a ray. And here I show you the most dense part is covers this equatorial part, which is in which the almost all mass is falling. No? Here we have an empty region, and here we get increasing of density. Progenitors are producing different jet geometries. We are observing that. And also how we can predict, well, roughly speaking, this could be a prediction for jet emission, the luminosity of the jet, which contains every component of the energy. We can see the variability to the instabilities in the accretion disk, basically. You can, if you remember, at the beginning, I showed the variability of the light curves. Yes, in this way, the reason is because instabilities, and this is the distribution, the angular distribution of the energy. And it is helpful to estimate the future electromagnetic counterparts. Yes, in the last part. Okay, got much information. In the last part, I want to present some preliminary results. Well, that was supported by the science competition. Yes, because we are looking for what kind of another not photonical signal, no, from gamma ray bursts, just for help us in the future to understand better, no, the physical properties of gamma ray bursts. And we are interested in how much energy is extracting from the central energy, what is the size of progenitors, durations.
Very beautiful pictures, but can you explain how do you get the formulas, the results? What equations are you solving?
To mention that. Yes, just here plenty of you are experts in general relativity. I will be.
I am not an expert, but I would like to see the equations, not the pictures.
Yeah. Yes, I will see the equations. Also, I can't do that. Yes, so yeah. Here I want to mention that I will be showing the polarization of gravitational waves, which is obtained by extracting by the transverse traceless.
But to get the radiation, you must have the source. On the right-hand side of Einstein equation, there is a source.
Yes, I will be showing that. Yes. Okay, but from that, I have to say that it's so far it's very, yes, as you know, it's very challenging to detect the strain of these gravitational waves because it's normalized by, the distance of the source is very far.
I'm not interested in normalization. I just want to see the equations. You have some pictures, what they represent.
The equations of the structure were shown during the previous part.
What equations?
That equation.
Yes, I will show.
Gravitational waves are described by Einstein equations. Where are these equations?
Yes, but let me start with orders of magnitude, no? Just for, because we are also thinking about detectors, no? And first of all, it's important to speak about the order of magnitude, no? Because we can take the most complicated estimation, but if it's not observable, well, it's wasting time, no? So yeah, so far, yes, I have to say that the frequency and the orders of magnitude of the characteristic strain that we can observe now is in this order of magnitude, no? But so far we can observe very high frequency sources, which belongs to compact binary mergers, basically. But nowadays we are expecting another sources, which could be emit in low frequencies. These sources could be arising from type 1H supernovae, extreme mass radiation spirals, and massive binaries. But our concerning now is gamma ray bursts. No, what is going on with gamma ray?
This still does not explain my question.
Yeah, with a minute, I will be showing some equations. So the problem here, I want to remind you that the first emission we can see from GRBs start to 10 to 15 centimeters. But before, we are blind to the electromagnetic counterparts because we have high opacity in the environment, and we can not see directly, no, from electromagnetic counterpart. But the question here is gravitational signals could do that or not? So far, there are, but I have to distinguish between which kind of source we can in which we can extract this information. There are several works nowadays discussing that the convection before the collapse of the iron core had potential source of gravitational waves because are very dense regions, and yes, we have a lot of instabilities here, and also in accretion disk. These works have been published. Well, this work is a little bit not all, but in this year we see this estimation. So I have to say that I am excluding that, no, because from this event we can observe gravitational waves from the collapse to the iron core to black hole, or this phase of instabilities, or the accretion disk. I have to say that I am using for this estimation an analytical solution taken from classic works. Basically, we noticed that people were discussing the.
But this energy momentum tensor is for a single particle. What particle
Yes.
is it? One
Yeah,
particle.
it's a blob of gas moving very fast. No?
This is a trajectory of one particle.
Yes, yes.
So which particle it is? Is one particle describing this whole complicated system? Doesn't make sense.
Yes, in this work, our particles are parcel of gas.
But there's only one particle here.
Yes. There is only one particle, but we can summarize the emission of every gas parcels. And we were precisely doing that. Well, the most complicated part of those equations are set the geometrical.
I understand, but physically it does not make sense. You have one particle and you use this one particle to model this complicated system. How do you know that this has any meaning?
No, the whole system is divided into several particles, and then
several.
we sum the
Therefore,
sum.
so
So
what is the motion of these particles? What are the trajectories of these particles?
Well, yeah, let me explain.
Where they come from?
They don't interact.
From the previous simulation.
Yes, this is the
But the
plan.
simulation did not include single relativistic particles.
Yes, because my simulations are, the gas is moving at.
What are the masses of these particles? What are the trajectories of these particles that enter in the definition of the energy momentum tensor?
I suspect that it's simply integrated out.
Yeah.
This is some kind of fluid approximation. So
Exactly.
this central energy tensor, which was written here, is just for one particle. But in practice, it's treated as a fluid, which is made as a collection of these particles. So there is an implicit integral over there.
So how it works, I have huge system, I divide it into small blocks.
Yes, exactly.
And then I
The motion is fixed by the previous
You have this-
pressure
yes.
gradients, whatever you
And
have.
And the question only by them is for giving
Yes,
some
And then
contribution to the.
integrate the motion.
Yes, this is, I think, just Green's function formula. It's because the Green's function for the gravitation.
Exactly, it's the green solution, yeah. Yes, it's
Okay.
yes, it's the Donald Richards solution, general. Yes, that's the idea. I think this cartoon, yeah, sorry for many cartoons, but I understand. But yes, if you want to see the whole equation, go to the paper. Well, from the simulations, we have many fluid parcels. No? And we know from each parcel the velocity, the energy of this fluid parcel, the direction of the velocity, which is important not to do this geometric estimation because we have to know which direction is the velocity vector pointing. we can extract from simulations velocities, energies, and take the contribution of all fluid parcels. But first, we have to do simulations, and after that, the extraction of the gravitational radiation. Yes, this is the map. Here I am showing you different scenarios, physical scenarios. A jet, successful jet, jet plus supernova, a failed jet, and a supernova explosion. And after that, I did the extraction, no? By this analytical solution. I applied to every fluid parcels. And just for do a test, for example, we since the equations say that the energy and velocity are the main physical contributions for this signal, this particular signal, we can verify in which regions are this gravitational wave arising, at least with this approximation. No? Here, these maps are maps of force velocity, which is the velocity times enthalpy. These maps enclose information in which the red parts contain the more energetic material and faster material together. And here I can show the evolution of this jet. Just since the jet is the shock front is pushing the heavy material of the star, the shock front is slow, but the material behind of the jet is very fast. And in some moment when the jet is breaking out the star, the fast and energetic material is converted in this kind of shell. And we can see the thin shell is we can see the thin shell, no? With this signal.
Sure, because my subject, I used the fact that the gravitational wave is emitted because of accelerating and big masses. In this case, I have this emitted jets, so there's a lot of mass, accelerating, and then different parts.
Energy, we have a lot of energy, these jets, because the density of the jets are not huge. They have a lot of energy.
So what is the main source of this?
The jet core.
Can I comment? Can I comment? It's relatively simple. Sources you know are those which you get from something called the quadrupole formula.
Yes.
Which you can derive but under certain assumptions, but the motions are not relativistic. And here motions are relativistic. You have to go back to the Green's function formula and derive everything from the scratch, knowing the motion at each point.
This was the quadrupole moment, and then
so you could apply the quadrupole formula here, but it wouldn't give a very precise answer.
Yeah.
Yeah, but yet about the energy estimation, I mean, the jet is something which is confined in space. So if we have you mentioned that we can see probably gravitational waves, the moment of collapse of the star, right? But there is a huge mass which collapses in a very short time and produces, because of the density, that is a very energetic event. And then you have a jet which is in the first approximation just a line. So how much energy can this jet emit compared with the energy which is gravitational energy or kinetic energy which is released by the gravitational collapse of the star? What is the ratio? Because I suspect that the ratio is still lower. I mean,
Yes.
This is very energetic
If
event,
the
but
collapse is spherical symmetric, you have nodes.
no, I understand, but
Energy of the underlying supernova is much less than the energy of the jet.
Yes.
You observe supernova in coincidence with long GRBs, and the supernova are not as bright as the jet.
But I observed that in optical, not gravitational, right?
There's I think one more effect. The jet blows away matter from two parts of the star.
Yeah.
It changes very much the how do we call it, the mass distribution in a very short time. So I think this might be an important factor. The mass of the star is blown away from the axis, and the masses are rearranged in a very fast way.
That produces this
I think
quote-unquote quadrupole effect, right?
yes.
So they're relativistic. Now.
Yes, I would expect this type of quality. So from a sphere, you get something sparse.
Yes, I didn't apply the quadrupole. Just the green solution.
This would be more
Because
precise.
we were probably misled, because in your, this very nice simulation of this thing, you show something like quadruple, right, option, and that.
Because it is kind of a later stage to some extent. Well, you cannot do everything, it's self-processed.
But still, you may try to understand.
Yeah, thank you for the comments.
The crucial element for the observation is the spectral distribution. This is what
Yes, I will talk.
Nobel
Yeah.
Prize was for. The spectrum of gravitational waves.
Yes, I will show some yes, spectral distribution at the end. Yes, just because the question also is which detector can observe signals. But well, with the in general, we can see from the evolution of the signal what is happening, because well, at the end, our numerical simulations are some kind of virtual laboratory. No? We know how much energy we are injected, and we can set that. And at the same time, we are observing, no, that when we are turning off the central engine, so well, it's natural expect that the signal start to decrease, no? And the system start to lose energy when it gets the breakout. But the important here is to say that we can quantify some perturbation in these signals as a characteristical event or important event. If we know the ejection time of some of these sources, we can know the real mean lifetime of the central engine. Here we can know the size of the progenitor, and also here directly, no, before the electromagnetic signal estimation. Before that, we can know the acceleration phase of this jet. Well, this is just for changing models and the directions of observers. And yes, the detectability. Well, also I have to say that this detectability is estimated as it's not a toy model, but we have to do some assumptions. The first one is we assume that the interferometer for the estimation of this signal, the interferometers are very good. Which is not true. No? We have to add some sensitivity in the interferometers. But yes, for do this estimation, I call the detector language to only take the Fourier transform of the evolution of the strain multiplied by the frequency, the square root, and this is the so-called the amplitude spectral density. From this plot, we can see the detectability of this kind of events. Here in dotted and dashed line, in dotted line, I added the noise curves of current interferometers, ground-based interferometers, and this is a space-based, the dashed line. These are ALIA and some interferometers planned to be as a space shuttle. And the continuous color lines means the signal from these jets, from those jets, at different observation angles. The close to the core of the jet, we get the most prominent signal, and it decreases as the observer is far from the jet axis. The peak of frequency is at low frequency, but it is a technical thing. Well, let me mention this after. In detectability as well, this detectability is underestimated because we use the rate of detection of GRBs. But the GRBs detected as an electromagnetic counterpart. But however, the aim of this work is just to say also there are some GRBs that we are not observing, no? And this detectability could be better. But yes, as you can imagine, yes, this table is a little bit complicated. But yes, in the first columns, I am showing the minimum distance that you need to in megaparsecs that you need to observe these events. With LIGO, Virgo, Cagra, which are the current interferometers, you have to detect nearby in the galaxy, no? HRB, which is not probable. No? And also even frankly for LISA, it's not very good the distance, and it's possible with another future projects. Here is more understandable in the next three columns, in particular in this red square. Here, this rate is estimated assuming the minimum distance, how much GRBs could be observed. Yes, I mentioned, for example, this BPO is a Big Bang observer. This is a project planned to observe gravitational waves coming from Big Bang, but the sensibility could be enough for observe this kind of things, no? Roughly speaking. We can observe 7 GRBs per year or 2, depending of the angle of the observer. But yes, we have to be careful with the interpretation of this kind of signals, because I have to say that the estimation of this amplitude spectral density is linked again with the data that we have. I have to say that for the estimation of this Fourier transform, the time resolution is 0.5 seconds, which is very low, poor resolution, time resolution. Similar work published a signal in which they claim that this kind of observation could be doing by current rho-based interferometers. But the reason here is more technical because it's not probably is false, because they have, for example, more temporal resolution because they follow a similar methodology that us, but with snapshots with this crazy temporal resolution, 10 to minus 4 seconds. We use 0.5 seconds, and they use 0.25. But these kind of simulations are quite expensive. Another thing is that it's never observed this kind of GRB pool. It's very, very energetic and very, very close. No? But this is overestimation of the amplitude of spectral density. And now this year we were working in a new methodology just for do a better estimation of with very high temporal resolution. It's just to change the methodology. Now the current one is do as a first step the simulation. Second step the post-processing. I mean extracting the information from simulations, do the estimation of the signal, and the detectability. Sorry. And now the new methodology is to consist. We made a module that do the GW signals together with the hydrodynamical simulation. And now it's ready. But I have to say something. No? This is a comparison between the old estimation and the new estimation. No? We did this estimation together with the time step of the simulation. The time step of the simulation is very, very, very short. It is according of how much time takes the one fluid parcel traveling by the speed of sound 1 kilometer, for example. It's very short time. We can get from this time the evolution of this estimation. We can set by different resolutions. Here I am showing 10 to minus 5 seconds, but we have to say that we can get spurious oscillations, and we have to be careful with that. Sorry. Yeah. It's long. Yes. In final, the size of the grid can alter the. But well, I did different tests. or set a better estimation. Yes, this is a test, convergence test. The reason is that typically in hydrodynamical simulations, we did the following. No? We refine the center of the object because the region of interest is that, but now in the methodology, we are refining a lot, and it becomes better. So yeah, now this is the new amplitude spectral density. Okay, we can see more higher frequencies, but again, the peak of the frequency is in very low. And it's on my conclusion now. Sorry, I don't explain, but yeah, we follow this work the jet dynamics from small to large scales, and we estimate the gravitational wave signals from our simulations so far. Yes, with current and nearly future observations, probably it's not possible to see that, but maybe in 20 years will be. And thank you very much and thanks for your questions and comments.